Okay, so let us move on to problem number 5 of your quiz. But before that, let me have the problem number 4 since we have overlooked the answer because we have not divided or we have not considered the double action of the shear force on the bolt here. Although we have mentioned that in the problem, we have overlooked in our equation. So basically, to illustrate that, we have, okay, when we are going to have the reaction here, say for example, the reaction is this one at any direction because this is just rotating, okay? So I'll just label this as RA, okay? We have a counter force here. It will cut into 2, okay? Because RA here is the external forces, and as a response of this bolt, of course, this is locked into this clevis here. So the plate here will tend to cut this, or will have a 2 cut sections along the axis of the cross section. Say if this is V, we can relate the two. Okay, we can relate the two. What is the relationship? The relationship of the two is we have RA is being resisted by 2 shear forces. Now, applying the formula, we have tau is equal to shear all over shear area. Okay, so we have a limit of 80 megapascals on that reaction, and then the shear force is V, right? So we're going to express this one in terms of V. In short, shear force here is just the half of RA. Okay, so writing that, V is RA all over 2, and then we just carry that over. We have double the area at the denominator, or simply it came from dividing the force into 2 because of this. Okay, so I think we have derived already the value of RA, and the value of RA is equivalent to 16,948.02. okay, so we have that 80, and this is 16,948.02 divided by twice the area, and we have area for a circular bolt that is pi all over 4 times d squared. Okay, so by cross multiplication, we have d equivalent to 11.61 millimeters. So this is the answer, or the right answer for the problem number 4. So let us move on to the 5th problem. So for the 5th problem, as we can see here, we have bar BC is directly carrying the RC cylinder, which is resting also at the wall. Okay, and then we have a pin connection here at B. At the other edge, we have cable AC also supporting this one. AC is 75 millimeter in diameter, and also we have a limit for AC equivalent to 70 megapascal according to the problem. Okay, so here it is. And at the same time, BC has a weight equivalent to 100 kilograms. So our task is to determine how heavy is the RC pipe that could be placed in the system without breaking the cable AC. Okay, so as a matter of solution, we should relate now the weight of the cylinder to that of the cable AC. Why? Because weight is unknown and AC has the limit or has the allowable. Or in short, W, although indirectly, will have an implication on breaking AC. Okay? So, where shall we start? Of course, we'll start with the free body diagram of the cylinder. So, I'll just have to draw that one. Okay, let us draw the FBD of the cylinder. Say FBD of the cylinder. Okay, so I'll just have to create an X and Y axis. Okay, because we have here concurrent forces. When we say concurrent, the force will meet at the same point. So by that, let us now have the forces. Number one, we have here the weight. Okay, so the weight is always going down. So there's no diagonal weight, or there is no upward weight, or there's no sideward weight, although weight has its component. So we're going to get that by and by. Okay, so in here, I'll just label this as weight. What else? Okay, if we have our an object that is resting on floor or any surface or a contact surface, there will be what? There will be a normal force or reaction. So what is the orientation of that reaction? It is always perpendicular to the surface. So whatever is the orientation of the object resting on that wall or on that surface, no matter what is the angle, no matter whether it is a circular one or not, it is always, the normal force is always perpendicular to the wall or any surface. In short, if we have this cylinder, it has a normal force on the wall like this, perpendicular. As we can see, it is perpendicular to the surface. Okay, at the same time, this cylinder is also resting on this inclined surface. So therefore, this is perpendicular line and this is the reaction. Okay, so let me have here a label for those forces. Say this is the reaction at wall, say RW, and this is the normal force of BC. Okay, the normal force of BC. Okay, so I think we'll just place that here because eventually these forces will meet at one common point, or as I have said, that these are concurrent forces that will certainly meet at one common point, and then we'll just use this X and Y axis. Okay, so this is now our okay, normal at BC. Okay, what else? We have here the reaction at wall. Okay, So our problem is, if we establish a section method or joint method, we should know the angle of a certain inclined member. W here is coincided with Y. RW, or the reaction at wall, is coincided with X. Okay? And this one, this is normal force diagonal. So that's it, diagonal. If we have diagonal, think of it that it should have an angle. Okay? It should have an angle. Why do we need the angle? In order to come up with its vertical, horizontal component, or a component that is parallel and perpendicular to a certain member. Okay? So in this case, the normal BC is perpendicular to BC. Remember that. That is perpendicular to BC. Alright? So we need the angle before we can transfer it to the bar itself. Okay? So what is the angle? Now, let us have a review on your trigonometric angle. So we simply have an incline. If we have an incline, there will be a reference angle. Whether the reference angle will come from the horizontal or the vertical. Say in this case, I'll just have the horizontal. Okay. So if we have to draw a perpendicular line to this inclined member, perpendicular, we'll just pair it with a vertical line. Say this is a vertical line. The angle between them is also the angle referred from the horizontal line to the inclined member. Okay? So again, we have here a diagonal, inclined at horizontal. Okay, say that is, name that. And then perpendicular and vertical, this is the angle also. So that is basic. Another thing, if we have an inclined, of course there will be an angle with respect to the horizontal. Any line, okay, at any line, horizontal line that is constructed within this diagonal line, the angle between them is always this one. Okay, and then if we have a diagonal again, if we wanted to refer to the vertical, say this is the slope, vertical, theta, slope, vertical, theta, slope, vertical, theta, slope, vertical, this is theta. Okay, that's it. That is so basic. Okay, applying it to this joint, NBC, or normal at BC, is, remember, that is perpendicular to this one. Okay, so a certain extension of that, in order for you to understand, or no need to extend that one. What would be the pair of normal BC in order to have an angle of 38 degrees? Of course, the vertical one, right? As I have said, inclined, horizontal. Inclined, horizontal, this is 38 degrees. And then perpendicular plus vertical, perpendicular plus vertical, this is the angle, or 38 degrees. Again, this is perpendicular plus vertical, this is 38 degrees. So I hope that is clear. And then next step is to apply the summation forces vertical in order for us to express normal at BC in terms of W. So we'll just concentrate to the y-axis. Okay, so we're just concentrating to the y-axis. Okay, because W is within y-axis. Okay, so you know what to do. Summation forces along y is equal to 0. So we have negative W, an upward force, diba? Upward force of NBC, okay, component, that is what? Normal at BC times, this is adjacent to the reference angle of 38 degrees. If it is adjacent, then we use cosine. Okay, cosine 38 degrees. Alright. So I think that is equal to 0. In short, negative W, or say W, is equal to, or sorry, I'll just express this in terms of normal force. So the normal force BC is equivalent to what? W all over cosine of 38 degrees. Okay? So normal at BC is equal to W, because this will eventually transpose, the other side becomes positive, and then we eliminate cosine 38 by dividing both sides by cosine 38. Therefore, the normal at BC is W all over cosine 38 degrees. So this is just the start of the solution. Proceeding further, let us transmit forces to the member BC. See, this is the member BC. Okay, a nice red BC. Okay, so let us just apply here the principle of action and reaction. So NBC here will transfer to this bar. At what point? At 3 meters. So we're going to measure. This is 9 meters. This is 4.5. 3 is somewhere here, right? So this is the location of NBC. So I'll just express that in another color. See, this is normal at BC, perpendicular to the bar. Okay, so perpendicular to the bar. So I think we will just have this to be equal to W all over cosine 38 degrees, just as computed. Okay, next, what else? This is pin connected at this edge. Although we do not need this one, we still need to reflect it for our appreciation. We have here a vertical and a horizontal reaction. Perhaps we can assume a direction for that. Say, let us have here R. What is that joint? B. So that is joint B. So we have here R, RBX, and this is RBY. So what else? We have here the weight, because the bar BC, according to the problem, it has a self weight that is equal to how much? 100 kilograms. Okay, so that is 100 kilograms weight here. See, this is where is it? At the mid or at the centroid of this bar, of course. See, this is weight of BC, equivalent to 100 kilograms. It's 100 kilograms multiplied by acceleration due to gravity in order to have a force unit or the weight. Okay, next, what else? We have here what? Tensile. So tension at AC, isn't it? Tension at AC. So we know what to do now. Simply, we're going to have to take moments at B in order now to relate W and tension at AC. But before that, we need to determine distances here. Okay, so see in the given if what we have on the distance. On the distance, we only know that this is 9 meters, the length of the bar. But with an angle given, we can manage to determine the other dimensions with this angle here. So what we do, okay, just to project the right triangle here, okay, say label this as distance what? Distance A. So this is distance A and this is distance B. So what function? Because what we know here is the hypotenuse and the angle. So by function of cosine or sine, we can solve for either A or B. So by function of cosine 38, adjacent to that is B all over this hypotenuse. That is, I think that is 9 meters. Okay. So with that, B is equal to 9 cosine of 38. 9 cosine of 38 is 7.09. 7.09 meters. So we can obtain A by any function. So let me have another method for that. Say I'll just apply here, but by Pythagorean theorem. Okay, so by Pythagorean theorem, we know that this is the equation. Okay, C here is 9, right? We know, do we know A? A is unknown, 7.09 squared, and then A is equal to how much? 9 squared minus 7.09 squared, and we just have to square root. We have here equivalent to 5.54 meters. We have known the distances, then we are now ready to take moments. Okay, so are you ready to take moments? Let's go. Okay, so summation moments at B, sorry. Okay, we have here this force that is clockwise rotation, so it will have a positive cosine 38. What is the moment arm? From B to this one is 3 meters. Okay, and then how about this one? That is clockwise, right? We have 981. Of course, this is half of B, right? So let us have this 7.09 divided by 2. Okay, 981 times 7.09 divided by 2. What else? This AC minus tension at AC. What is the moment arm? From the perpendicular distance is A, right? So we have 5.54 meters. So shall we equate this to 0? Now, we have now the relationship between W and AC, which is actually our objective initially. So in order to solve for W, of course, we should know the value of TAC. How? We know that AC has the size, has the given size. And then we also know the capacity of AC. Then, with that, we'll just simply use the simple stress formula. Simple stress formula. Sigma is equal to P all over A. What is the sigma? AT. What is P? The tensile at AC. What is A? What is A? The cross-sectional area, which has a diameter of 75. Okay? So, we have here TAC. Okay, so TAC is, wait, I think 80 here should be 70, sorry. Let us just replace that one, right? 70. So how much is TAC? We have here 309,309, 250.53. Okay, so knowing that, you know the next step, just substitute here 309, 250.53, and then finally W is obtained. So we have 449,105.79 Newton. So it's the answer. Okay, so that's it for our solutions. So thank you. So have more practice and good day.